Invite next author, Examinioti, and she will present us microstructure and tensile mechanical behavior of laser beam welded AA2198 joints, effect of process parameters and post-welding treatment. Please.
Thank you very much, Mr. Chairman. My name is Examinioti, and I'm a PhD student of Lithium University, University of the Aegean, and Helmholtz Zentrum Institute in cooperation. I will first motivate, then explain the procedure, present the results, and finally conclude. Beginning with the technological problems, all traditional designs of aircraft structures have been made by fastening differential structures by riveting. It's obvious that riveting increases weight. New trend is, let's say, to replace rivets with fusion welding. By this, you can reduce the weight up to 15% and respectively cost up to 30%. Lithium is a metallic element with low density, and for that reason it was introduced to aluminum alloys to reduce weight. Nevertheless, this attempt had some disadvantages, such as higher anisotropy in the mechanical properties. 2198 is an aluminum lithium alloy, and it's in the third generation. This alloy is a precipitate alloy. By this I mean that with natural aging or with artificially aging, you can whatever the prostatic properties. And for example, for this alloy, you don't have only one mechanism, but you have 4 different. That means that makes the situation more difficult. But why we need these precipitates? Because they are blocking the dislocations. By blocking the dislocations, you can increase yield strength and you can sacrifice the ductility. Tensile mechanical behavior of various artificially aging times was examined in the literature. Here you can see that with increasing artificially aging, yield stress increases after 48 hours and additional structure decreases. For the experimental procedure, we investigate aluminum alloy 2198 with 5 mm thickness. We did laser beam welding for 2 different, let's say, parameters, for autogenous and for Fieldwire, and some of the specimens were heat treated. We just machined the tensile specimens in T direction, and we had the mechanical testing, the evaluation, and the conclusion. For the welding parameters, we used fiber laser machine with 8 kilowatt power, and we used argon as sealing gas. As I said, we had autogenous and Fieldwire. The Fieldwire material that we used, it was aluminum alloy 4047, which is silicon alloy, with 1.2 millimeters diameter. In all specimens, the weld was in the middle, in the center of the gate's length. Here you can see the tensile dimensions according to the STM specification. This is the oven that we did the heat treatments. And the heat treatments was at 170 Celsius, and we choose 3 different hours, 1 hour in each condition, for under-aging, peak aging, and over-aging condition. This is a testing machine of 100 kilonewton, and we used a laser extensiometer. For the experimental results and hardness measurements, autogenous specimens with heat treatment close to the weld. For this base material, high hardness values were noticed in the peak aging condition in 48 hours. For Fieldwire material, Fieldwire specimens with heat treatment, they have the same, they present higher hardness at the peak aging condition in 48 hours. And they have similar hardness results from the in the fusion zone. We did also EDX analysis for the fusion zone. We just collect 6 points, 3 in the bright areas and 3 in the dark areas for autogenous and for filler wire. Here we have let's say, the amount of the silicon, which of course in the fusion zone of the material with filler wire is higher. Also, we did EDX line scan analysis. You can see for autogenous and filler wire that the distribution of silicon, of course, is different. We have higher distribution of silicon in the fusion zone. For the tensile specimens, comparison of the unwelded with welded specimens. The non-welded exhibit higher tensile ductility compared to welded specimens. Autogenous with red specimens showed lower ductility, and specimens with filler wire showed higher yield stress and higher ductility. The typical tensile curves for autogenous laser beam weldings and with increasing artificial aging time. You can see that T3 condition exhibits lower yield stress and ductility, of course, compared to non-weld. With increasing artificial aging and under-aging condition shows higher yield stress and lower total elongation at fracture. With increasing again at 48 hours, the yield stress is slightly higher, and for 98 hours, and over-aging condition shows higher yield stress. On the other hand, for filler wire specimens and artificially aging, laser beam welding with filler wire presents lower yield stress compared to non-welded, and for under-aging condition shows a higher yield stress and lower ductility. And with increasing artificial aging in 48 hours, we had a slightly decrease in yield stress and ductility. And for overaging condition, shows higher yield stress. Let's sum up the results. So we have yield stress versus artificial aging time at 170 degrees. With black we have autogenous, and with red we have the filler results. Autogenous results seems to increase from 3 hours up to 98 hours, but for filler wire we have an continuously increase from T3 up to 98 hours, which is 30% higher compared to autogenous. Ultimate tensile strength versus artificial aging time. We can see that in both cases we have a continuously increase up to 98 hours. Ultimate tensile strength for filler wire specimen is 70% higher compared to autogenous specimens. Total elongation at fracture versus artificial aging time. I want to say that it's not 0. I didn't change the diagram. Autogenous, let's say the total elongation at fracture of filler wire specimen decreased approximately 83% from T3 condition up to 98 hours. So to sum up the results, addition of filler wire gives high tensile mechanical properties in T3 condition. Weldments with filler wire provide higher hardness values in the fusion zone due to the silicon particles. Both weldments for autogenous and with filler material are responding in the same manner to artificial aging. And post-welding heat treatment after the possibility to tailor yield stress over tensile ductility.